started with was exponential lambda t. So the solution I'm going to get for lambda 1 t, for lambda 2 t, for lambda n t. Now there is a principle of superposition. That means if you have a set of linearly independent solutions, the general solution yt of the homogeneous part you can write as C1 lambda 1 t plus C2 to the power lambda 2 t plus Cn lambda n t. Is there anyone who did not see such things before? Raise your hand. All of you have seen this? And can you tell me why these terms are linearly independent? Or what is the condition for them to be linearly independent?
You can't have a repeated root in lambda.
Yes. Anyone else? Can you tell me what happens if there are repeated roots? Suppose you have two roots repeated. Suppose you have lambda 1 and lambda 2 equal. Then clearly you don't have independent, two independent solutions, because e to the power lambda 1 t, say C1 plus C2 to the power lambda 1 t, you can combine to write C1 plus C2 e to the power lambda 1 t. Yes? Does this make sense to you? That if you have the one root repeated two times, you can simply add the constants up and write it in one term. So that means they're not linearly independent. And in such a situation, what you do, you need to, if there one root repeated twice, you do C1, let me write on the other board. One is repeated twice, so you get yt C1 plus C2t e to the power lambda 1t plus C3 to the power lambda 3t, like that, plus Cn e to the power lambda n. So the idea is you multiply by a factor of time. Okay. So you have C1 e to the power lambda 1t and C2 e to the power lambda 2t. These are clearly not linearly independent if both the roots are same, if the root is repeated. But if you multiply by a factor of time, now you cannot write this term as a proportional to this, some constant times this. Okay? So by multiplying with a t, I make them linearly independent. So that's how I do it. Don't like this idea? Okay. And what happens if I have, suppose the root is repeated k times? What do we do? It's the same strategy. So you do C1 plus C2t plus C3t square, blah, 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 up to ck to the power k minus 1. Okay. So depending on how many times a root is repeated, you need to keep changing the terms, like multiply by t squared, tq, and blah, blah, blah. Not too bad. So that's the homogeneous part. I have not touched on the inhomogeneous part yet. I'm going to come to that later. So always if you get linear, nth order linear ODE or second order linear ODE, the first thing to do, keep the right hand side 0, make it a homogeneous equation, and solve the homogeneous part using this method, and then go back to the non-homogeneous part later. So I have a few examples from the note. Suppose you have this very simple form d2y dt2 equals 0. And this you can solve simply by integrating it to 2 times. You can t equals c1 plus c2t. You don't even have to do exponential trial solution. Now if you have this d2y dt2 minus 2y 2 dy dt plus y equals 0, and you do yt equals e to the power lambda t. What's going to be the equation if lambda equals 0? So if I plug e to the power lambda t in this equation, I'm going to get lambda square e to the power lambda t minus 2 lambda e to the power lambda t plus e to the power lambda t equals 0. This implies lambda square minus 2 lambda plus 1 . So that tells me lambda minus 1 square equals 0. So you can think lambda 1, lambda 2, both are equal to 1. Okay. So now, following the recipe which I discussed on the top board, on the right top, so what should be the solution for the homogeneous equation? Just look at the repeated root solution. So as the solution here. So I have the root 1 repeated twice. And the solution is going to be c1 plus c2t, and then exponential of t. Do you follow? So c1 plus c2t, because the root is repeated and the root itself is 1, so I don't write it. So it's just e to the power t. So that's the solution of the homogeneous part. Now, if I have a complex root, and they typically appear in conjugate. So if you get a root lambda, you are going to get another root lambda square. And it always happens. It's not that it's a spatial equation. It always happens. So for example, if I get this equation, dy dy dt2 plus 9y equals 0, and I do e to the power lambda t solution, I plug this here, I get lambda square plus 9 equals 0. That gives me lambda equals plus minus 3i. Correct? So the solution you write, xt is c1 e to the power 3it plus c2 e to the power minus 3it. Are you with me? So do you know any other way of writing the same solution? You understand something? Back? Sine and cosine. That's exactly right. So these are the two relations you often encounter and you have to use. And it's not always easy to tell what I should expect you to remember on the test. I have seen like graduate students coming to me and saying, why should I remember this, because this is not part of ordinary differential equation or anything. So that's a difficult question to answer, but I would encourage you to remember this because it's often used in ODEs and PDEs. So if you use these two, are you, for example, first, do you know these two relations? Are you, all of you have seen this? Exponential ix is cosine x plus I sine x, yes? So if you replace this 3it and negative 3it by these expansions, you are going to get c1 prime cosine 3t plus c2 prime sine 3t. Are you okay with this? Yes? If you cannot see this step from here, tell me. I'll explain it a little bit more. Are you okay? I just use this. Instead of ix, I use 3it and replace x with 3it. That's all it is. Okay? And c1 prime involves a combination of c1 and c2. Okay. And if the roots are of this form, if you see, instead of simple imaginary roots like this, you might have a little bit more complicated. So for example, you might have if you have roots a plus minus bi, if you have those roots, then your yct can write as c1 e to the power at cosine bt plus c2 e to the power at sine bt. So if you have not a pure imaginary root,